In this section, we will discuss canonical representations of infinitely divisible distributions. Or more precisely, we will describe the most general form of either a Laplace transform or characteristic function of such distributions. And once we know this most general form for either Laplace transform or characteristic function, we will be able to describe all possible canonical ways to construct infinitely divisible random variables. Now, we will begin with the case of non-negative infinitely divisible distributions, or random variables. So if x is non-negative random variable with infinitely divisible distribution, then in this case we will describe its Laplace transform. So in other words, for all non-negative t, we will take a look at the expectation of e to the minus tx. And we will show that the most general form for the Laplace transform is exponential minus some constant beta times t, and then minus the integral from 0 to infinity of 1 minus e to the minus tx d mu of x, okay, where beta is a non-negative constant and mu is a measure on 0 infinity, such that the integral of the minimum between x and 1, so in other words function x truncated at 1 with respect to this measure mu, is finite. Moreover, such a representation is unique, and moreover all such functions of this form correspond to some infinitely divisible distribution on the positive half line. Now, I'm not going to discuss the proof of this theorem here and refer to the notes, because its proof is actually almost identical and actually simpler than the proof of the general case that we are going to discuss next. And I will only mention this last point, that all such functions correspond to infinitely divisible distributions, because we actually already know what these random variables look like. So more precisely, the proof of the last claim, what we need to notice is that if we take pi to be a Poisson process with the mean measure given by mu, so that's a Poisson process on 0 infinity, and then consider a random variable given by this constant beta plus the sum over all points in this Poisson process of x, then this is actually a random variable that has Laplace transform as above. And we know this from Campbell's theorem. Right? Namely, the condition here that the integral of x truncated at 1 with respect to this measure mu is finite was the condition in Campbell's theorem that ensures that the sum is well defined or is finite almost surely. And then of course the term minus beta t in the above representation just corresponds to this constant beta, and the second term given by the integral is exactly the representation for the Laplace transform in Campbell's theorem for this sum. So in other words, this theorem here that we don't prove plus Campbell's theorem tell us that the most general way to construct infinitely divisible non-negative random variables is take a Poisson process on the positive half line and just sum the points in that process. Okay, and also add a constant. Okay, so next we will discuss the general case of signed random variables, or infinitely divisible distribution on the entire real line. In this case we have the following result. If a random variable x is infinitely divisible, then its characteristic function has the following form. You can have it times some constant gamma, so this just corresponds to having a constant in your random variable. Then minus t squared sigma squared over 2, which we can recognize as the characteristic function of a Gaussian random variable with variance sigma squared. Okay, plus the integral over the real line excluding 0 of the following function, e to the itx minus 1 minus itx, indicator that x in absolute value is less than or equal than 1. With respect to some measure mu of x, where, as I said, constant gamma is just arbitrary constant, sigma can be taken to be non-negative, and mu is a measure on the real line excluding 0 that satisfies the following condition, that the integral over the real line excluding 0 of x squared truncated at 1, so in this case, by comparison with the previous result, we have x squared instead of x. Right? When you integrate it with respect to this measure, this should be finite, and moreover, this representation is unique. Okay, it is also true that all such functions as above correspond to infinitely divisible distributions, but we will postpone it to the separate result so that we can discuss in more detail the role played by all possible terms in this construction or in this representation. Okay, now let me mention here that this measure mu in the above representation is called the Levy measure of this distribution, or the Levy measure of this random variable. And now the reason we exclude 0 from the real line above is because in both integrals, right, in the above integral in the representation, and also in this integral in the condition for this measure mu, this Levy measure, the integrand at 0 is 0. So the reason we exclude 0 is just for the sake of uniqueness. So if you like, you can consider the measure on the whole real line and write the integral on the whole real line, but in this case the measure of 0 will not be really determined. So if you want to have uniqueness, you can, for example, just enforce that the measure of 0 is 0. Now another comment is that in the above representation we have this indicator that x is less than or equal than 1, and the choice of the constant 1 here is also arbitrary. You can see that if you replace constant 1 by 2 or any other constant, the piece of the integral where you have that indicator is of the form I times t times some integral, which will be just it times some constant. So redefining this constant 1, it will be just redefining the constant gamma. Right? So you can move part of that integral by changing the indicator into the definition of the constant. Okay, and just for certainty, in this representation we fix the interval to be between -1 and 1. Okay, and now let's discuss the proof of this theorem. Okay, and so to prove this result, we will actually continue where we left off at the end of the last section and use this representation of the characteristic function of an infinitely divisible distribution as a limit of compound Poisson. Or more precisely, as a limit of characteristic functions of compound Poisson, which was of this form, and where Pn was a distribution such that the n-fold convolution of Pn is equal to our distribution P. And then using this representation, our proof will consist of 2 steps. So in step 1, we are going to extract some information from this representation. And more precisely, we will show that if we consider the following sequence of measures Gn on the real line, given by rescaling x squared truncated at 1 of this measure n times dpn. Okay, so in other words, it's just a measure n times pn, which is rescaled in the neighborhood of 0 on the interval from -1 to 1 by x squared. And we will show that with this rescaling, this sequence Gn converges over some subsequence nk to some finite measure on the real line. Okay, so we can see that the measure Pn is a probability measure, so scaled by n, the total mass is n, but basically when n goes to infinity, the mass concentrates near 0. And so this scaling by x squared near 0 will ensure that the total mass of the sequence of these measures is uniformly bounded, and also it's a uniformly tight sequence, so by selection theorem we'll be able to choose a converging subsequence. Okay, and then in step 2, we will basically just plug in this information that we obtain in step 1 into the above representation for the characteristic function, and our claim will come out after some basic manipulations. Okay, and let's begin here with the proof of step 1, where we will actually use only the real part of the above equation. Okay, namely, I'm going to take a real part on both sides and then take log and put a minus sign. So it will be convenient to look at this kind of representation. And one can see that in this case, the above equation becomes the limit of n times the integral of 1 minus cosine of tx with respect to this measure Pn is equal to minus log of the modulus of the characteristic function f of t. Okay, and using this equation, we want to control this sequence of measures Gn or nPn separately in the neighborhood of 0, where this rescaling by x squared will come out, and away from 0. So first, let's consider what's going on in the neighborhood of 0, so when x is less than or equal than 1. Okay, so in this case, we will actually first just take t equals to 1. And so the above limit tells us that when we look at n times the integral of 1 minus cosine of x with respect to this measure Pn, now in the limit it will be equal to the right hand side above. But I want to say that for large n, this will be bounded by the right hand side plus arbitrary epsilon. In fact, here I'll just take plus 1. At first step, we'll just need that it's bounded by some constant for large n. But on the other hand, we see that on the left hand side, when we integrate 1 minus cosine of x, well, first of all, it is non-negative. So if we restrict the limits of integration to an interval from -1 to 1, we will get a lower bound. But also because in this first step I'm interested in this interval from -1 to 1, 1 minus cosine of x on that interval is actually of order x squared. And since I want the lower bound here, one can check that it's bigger than x squared over 3 when x is between -1 and 1. Okay, the constant here doesn't matter, but I'll just write it to keep this equation clean. And so as a result, we get the lower bound on this side of the form n times the integral between -1 and 1 of x squared over 3 with respect to this measure p. Okay, and let's just say that this gives us that the n times the integral between -1 and 1 of x squared with respect to this measure p is bounded by some constant, finite constant for large n. So you see, this gives us control of this sequence n times the measure Pn rescaled by x squared on the interval -1 to 1. Then in the second step we will try to control outside of this interval. And here we cannot use the above equation directly in this way because cosine actually will be close to 1 when x is large. So we cannot bound from below directly, but the trick here is to take arbitrary small delta and then average the above equation on the interval from 0 to delta. More precisely, this will mean that 1 over delta, the integral from 0 to delta of n times the integral above, and we average in the parameter t, and in the limit this goes to the average of the right hand side, but again I'm going to say that if I add arbitrary small epsilon to the average of the right hand side, we get this inequality for large enough n. But then if you interchange the integrals on the left hand side, because we are integrating non-negative function, and compute the integral in t, you get that the left hand side is actually n times the integral of 1 minus sine delta x over delta x with respect to this measure Pn. And I leave the right hand side as it is. And in this form we will get control that we want outside of the interval -1 to 1, because, well, first of all, sine of x over x is always bounded by 1 for all x, so the integrand on the left hand side is non-negative and we can restrict to any interval to get the lower bound. But also when delta times x is bigger than 1 in absolute value, one can see that the integrand is actually greater or equal than 1/2. So outside of the interval -1 to 1, sine of x over x actually becomes separated from 1 by at least 1/2. So if we use this information, we get a lower bound on the left hand side of the form n times integral over x greater than 1 over delta of 1/2 with respect to this probability measure Pn. Okay, so in other words, this is just n times Pn of all the values x greater or equal in absolute value that 1 over delta. Okay, and this is bounded by epsilon minus the average. Okay, and then we see that if we take delta equal to 1, we get that n times Pn of the complement of this interval from -1 to 1 is bounded by some constant, so another finite constant. In particular, if we recall that we define the measures Gn above by scaling n times the measure Pn by x squared in between -1 and 1, well, what we just showed is that for large n, the total mass of these measures is bounded by some finite constant. In other words, the total mass for the sequence of these measures is uniformly bounded for large n. Okay, and the second piece of information we want is uniform tightness. And for this, of course, we notice that the log of the absolute value of this characteristic function at 0 is, of course, just log of 1, so it's 0. So we can take delta small enough, okay, so that the average over the interval from 0 to delta by continuity of the characteristic function is as small as we like, so less than epsilon. Okay, and so using the above equation for this delta shows that n times the probability for x greater in absolute value than 1 over delta is less than or equal than 2 epsilon. And of course, this is the same as Gn of this set is less than or equal than 2 epsilon. Okay, for large enough n. So we showed that for every epsilon we can find a compact, so that for large n, these measures outside of the compact carry small weight less than epsilon. Okay, so this shows uniform tightness. Okay, and this means that we can now apply selection theorem and conclude that this sequence of measures converges to some finite measure weakly over some subsequence. Okay, so this concludes our step 1, and now we will see how this information will imply our representation that we want. Okay, so for this, let's go back to the equation that we started with, that n times this integral converges to the log of the characteristic function. Okay, so instead of writing exponential, just for convenience, I take the log of both sides. And now let me rewrite the left-hand side in terms of this sequence. So we have to rescale by x squared on -1 to 1. That means I have to multiply and divide by x squared truncated at 1, and then what is left is exactly the measure Gn. Okay, and since these measures converge to this finite measure over some subsequence, we want to understand why this implies convergence of this integral. Now, the problem here is that when you look at this function e to the itx minus 1 and you start expanding it in Taylor series, the next term will be itx, then you will have t squared x squared over 2, and then you have some lower order terms. So actually, near 0, this function is of order x, and in the integral we divide by x squared. So the way it's written now, the function actually blows up at 0, and so it's not a continuous bounded function. We cannot conclude that the integrals converge. And so the trick here is to remove this term, so to remove this singularity by defining a function hx of the form as above, with this term itx removed in some neighborhood of 0. So on the indicator when x is smaller than some constant c. Okay, and in a second we'll choose this constant appropriately. And let's also include the rescaling by x squared truncated at 1 into this function. Okay, so we see that removing this singularity, we can actually extend this function by continuity to 0 if we define it there to be minus t squared over 2. Right, so then this function is continuous near 0, but of course we created a jump at plus and minus c because of this indicator. And also, since we subtracted, we have to add this term. But in any case, let's rewrite the above integral by adding and subtracting this term. So the above integral can be written as a sum of two integrals. So the first integral will be with this term subtracted, so it's just hx with respect to the measure Gn. And since we subtracted, we have to add back this term itx on the interval between minus c and c. Okay, but the good news is that in the first integral, this function h is now bounded, and its only discontinuity is a finite jump at plus and minus c. So if we take here c to be such that both minus c and plus c are points of continuity of the limiting measure g, okay, then it doesn't matter that we have a finite jump there, and we can conclude that the convergence of these measures over a subsequence implies convergence of these integrals. Okay, again over some subsequence. But recall that the sum of these two pieces above converges to the log of the characteristic function. And so if the sum converges and the first piece converges, it forces the second piece also to converge to something along the same subsequence. But we can see that the second term is of the form I times t times something independent of t, so this has to converge to some constant, let's call it gamma, that depends here only on c and of course on our sequence gn. And so in the limit, the sum of these two pieces can be written as a sum of these terms like this. And of course what this means is that, remember, the limit was the log of the characteristic function, so now we wrote it as it times some constant plus this integral. So now let me write it explicitly again. Okay, in terms of this limiting measure g. And now we are almost done. So first, like we mentioned above, we can replace the interval from minus c to c now by any other interval. So if in the second term you replace c by 1, these two integrals just differ by a constant of the form I times t times something. Okay, so that will just result in redefining this constant gamma c by some other constant gamma. Now second, although our measures gn before the limit carried no mass at 0, after taking a limit there could be some mass accumulated, and let's denote that mass by sigma squared. And because our integrand here by continuity was defined to be minus t squared over 2, so if we separate 0 from the integral, right, we can write the integral over 0 as minus t squared over 2 times sigma squared. Okay, so that's how the second term comes out. And then we are left with the integral over the real line excluding this point 0 of the same thing. And finally, it remains to just rename the rescaled measure in that integral. So if we denote by d mu this measure in the above integral on the real line excluding 0, then of course we see that the integral over the real line excluding this point 0 of x squared truncated at 1 with respect to this measure mu, this is just an integral with respect to the measure g, and so we get that this is g of the real line excluding 0, and since measure g is finite, this is finite. And so if we rewrite the last integral in terms of this measure mu, we finally get exactly the representation that we want. Okay, so this finishes the proof of this representation, and it only remains to show the uniqueness. Now, for the uniqueness, it will be actually convenient to go back to this representation here before we separated the mass at 0. So in this equation, the right-hand side is written in terms of two parameters, this constant gamma and some finite measure g on the real line. Okay, and so this combination is expressed in terms of the characteristic function. And somehow we want to show that this implies that the choice of gamma and g here is unique. So here we will use that the dependence of this first term on t is linear. So we'll use this trick that if you take the above equation at some t and then compare it with the average of the same equation between t minus 1 and t plus 1. So the linear part with gamma will cancel out by this transformation and will be only left with the integral term, and you can check that it will become the following integral. Okay, it's just straightforward to check that, so I will omit this here. Now, if you look at these two factors here, first of all, we can see that this is non-negative. And then if we extend it by continuity to 0, so one can see that it should be set 1/6 at x equal to 0. Okay, then this is actually a continuous bounded function on the real line. So that means that we can think of it as some kind of change of density. So we can define a measure f by this change of density of our measure g. And since our measure g is finite and this factor here is non-negative and bounded, this f is also a finite measure on the real line. Okay, so the above integral is actually just a characteristic function of some finite measure on the real line. And since by this equation it's completely determined by the characteristic function f of t of our distribution, this characteristic function uniquely determines f. And of course, once we know f, we know measure g. The measure g at 0 gives us sigma squared, and the original equation, there is only one term left, so that means we know gamma. Okay, so this shows that this representation is unique, and so the proof of this theorem is complete. And so what remains is to show that all such representations correspond to characteristic functions of some infinitely divisible distributions, which will be done in the next video.